Space, the final frontier, a canvas of darkness sprinkled with the brilliant light of a billion stars. It beckons us, calls to the explorer within, yet within our history lies a paradox. We reach for the stars, but we also build weapons capable of unimaginable destruction. Nuclear weapons, a testament to our ingenuity and our capacity for self-destruction. What if the biggest one detonated not on Earth, but in the cold vacuum of space? Imagine, if you will, the searing heat of a billion suns unleashed in an instant. The blinding flash, a silent scream of energy ripping through the cosmos. Nuclear explosions are a force of nature we have managed to bottle, but their effects in the vacuum of space are far different from the fiery chaos we associate with them on Earth. To understand what happens, we need to journey into the heart of these weapons, to the realm of atoms and the forces that bind them. The cosmos, vast and mysterious, holds the answers to the ultimate power we wield. Nuclear fission, the process that powers these weapons, is the splitting of an atom's nucleus. Think of it as splitting a log. You get energy out, in the form of heat and light. But when we split an atom, the energy released is millions of times greater. This energy, in a bomb, is uncontrolled, instantaneous and devastating. On Earth, the devastation is multifaceted. The initial blast, the searing heat, the shockwave that flattens everything in its path. Then comes the radiation, the invisible killer that lingers long after the firestorm has passed. But in space, a very different scenario unfolds. A scenario where the very things that make nuclear explosions so destructive on Earth are absent. In nuclear fission, neutrons collide with the nucleus of an atom, causing it to split. This splitting releases more neutrons, which then split more nuclei, creating a chain reaction. In reactors, this process is controlled to produce energy. In bombs, it's uncontrolled, leading to massive explosions. The implications of nuclear fission are profound, from energy production to the potential for unparalleled destruction. Space, unlike our planet, is a vacuum. There's no air to carry a shockwave, no oxygen to fuel the inferno of a firestorm. The familiar mushroom cloud, that chilling symbol of nuclear devastation, wouldn't exist. Instead, the energy from a nuclear explosion in space would radiate outwards in a sphere, an expanding bubble of deadly radiation. This radiation, primarily gamma rays and X-rays, poses the most significant threat. Unlike the heat and light, which dissipate quickly, these invisible rays can travel vast distances, potentially damaging or destroying satellites and spacecraft caught in their path. The very technology we rely on for communication, navigation, and even monitoring our planet could be crippled by a single, high-altitude detonation. On Earth, a nuclear explosion unleashes a shockwave and firestorm, devastating everything in its path. In space, the lack of atmosphere means no shockwave, but the radiation threat is far-reaching. Earth's atmosphere offers some protection from radiation, but in space, there's no such shield. A space-based nuclear explosion could disrupt global communication networks affecting millions. Scientists would need to monitor and track the radiation effects to mitigate the damage. Section 4. Silent but deadly. The ripple effect in space. The potential damage to satellites highlights another critical difference between explosions in space and on Earth. In space, there's no atmosphere to absorb the energy, no ground to contain the fallout. The debris from a nuclear explosion propelled by the initial blast would become a silent swarm of shrapnel hurtling through space at incredible speeds. This debris could pose a significant hazard to other spacecraft and satellites, potentially triggering a chain reaction of collisions known as the Kessler syndrome. Imagine a cascade of debris, each piece capable of destroying a satellite, creating more debris and so on. It's a domino effect with the potential to cripple our space infrastructure and trap us on this planet for generations. Additionally, the electromagnetic pulse, EMP, from the explosion could fry the electronics of satellites and spacecraft, rendering them useless. This would disrupt global communications, navigation systems, and even financial networks, causing chaos on Earth. Scientists would need to analyze the data to understand the full extent of the damage and develop strategies to mitigate future risks. The ripple effects of a nuclear explosion in space are far-reaching, affecting not just the immediate vicinity, but potentially altering the course of human progress in space exploration. Section 5. Space, the final frontier, but at what cost? During the height of the Cold War, the specter of a nuclear conflict hung over humanity. We conducted tests, witnessed the destructive power we wielded, and hopefully, learned from our mistakes. Treaties were signed, limitations were imposed, and while the threat remains, the world recognized the need for control. But as we venture further into space, as we establish a more permanent presence off-world, the question arises, can we prevent the mistakes of the past from haunting our future among the stars? The vastness of space may seem like a safeguard, a buffer zone that can absorb our worst impulses, but as we've seen, the reality is far more complex. Nuclear detonations in space, while visually different, pose unique threats, not just to our technology, but to our aspirations of becoming a spacefaring civilization. The cost of such detonations is not just immediate but long-term, affecting our future missions and the safety of space travel. As we continue to explore the cosmos, let's hope the lessons learned from our past can guide us towards a future where the stars reflect our hopes, not our fears. Gap 3s, nuclear fusion, the process that powers the stars, is the combining of atomic nuclei. Unlike fission, which splits atoms, fusion merges them, releasing even more energy. This process powers our sun and holds the potential for a nearly limitless energy source. But harnessing fusion on Earth has proven to be a monumental challenge. In space, the conditions are different, and the potential for fusion-based propulsion systems could revolutionize space travel. Imagine spacecraft powered by the same process that fuels the stars, capable of reaching distant planets and beyond. The implications for our exploration of the cosmos are profound. Gap 3s. The potential for nuclear technology in space extends beyond weapons. Nuclear propulsion systems could drastically reduce travel times to distant planets, making manned missions to Mars and beyond more feasible. But with this potential comes responsibility. The same technology that could propel us to the stars could also be used for destruction. As we advance our capabilities, we must ensure that our use of nuclear technology in space is governed by principles of peace and exploration, not conflict and destruction. Gap 3s. As we venture into space, we must consider the ethical implications of our actions. The use of nuclear technology in space raises questions about the potential for contamination, the impact on extraterrestrial environments, and the long-term consequences for humanity. We must balance our desire for exploration with our responsibility to protect the cosmos. The decisions we make today will shape the future of space exploration and our place in the universe. Let us strive to be stewards of the stars, ensuring that our legacy is one of discovery and respect for the vast, uncharted frontier that lies before us. Gap 3s. The future of space exploration will require new treaties and agreements to govern the use of nuclear technology. International cooperation will be essential to ensure that space remains a domain of peace and scientific discovery. As we look to the stars, we must work together to establish guidelines that prevent the weaponization of space and promote the responsible use of nuclear technology. The challenges are great, but so too are the opportunities. By working together, we can ensure that the final frontier is a place of hope and possibility for all of humanity. Gap 3s. As we stand on the brink of a new era in space exploration, we must envision a future where humanity thrives among the stars. A future where we harness the power of nuclear technology for the betterment of all. Where we explore the cosmos with a sense of wonder and responsibility. The journey ahead is filled with challenges, but it is also filled with promise. Let us embrace the spirit of exploration, guided by the lessons of our past and the hope for a brighter future. The stars await, and with them, the endless possibilities of what we can achieve together.